Hi everyone, this is Glenda Ganzon and welcome to my Human Anatomy and Physiology class. And for today's lesson, I'm going to discuss the building blocks of matter, which are the elements and atoms. Matter is anything that occupies space and has mass. An object's mass and its weight are related concepts, but not quite the same. An object's mass is the amount of matter contained in the object, and the object's mass is the same whether the object is on Earth or in the zero-gravity environment of outer space. An object's weight, on the other hand, is its mass as affected by the pull of gravity. Where gravity strongly pulls on an object's mass, its weight is greater than it is where gravity is less strong. An object of a certain mass weighs less on the moon, for example, than it does on the Earth because the gravity of the moon is less than that of Earth. In other words, weight is variable and it is influenced by gravity. A piece of cheese that weighs 1 kilo on Earth weighs only few kilograms or ounces on the moon. All matter in the natural world is composed of one or more than 92 fundamental substances called elements. And what is an element? An element is a pure substance that is distinguished from all other matter by the fact that it cannot be created or broken down by ordinary chemical means. While your body can assemble many of the chemical compounds needed for life from their constituent elements, it cannot make elements. They must come from the environment. A familiar example of an element that you must take in is calcium. So, what is a calcium? It is essential to the human body because it absorbed and used for a number of processes including strengthening bones. When you consume dairy products, your digestive system breaks down the food into components small enough to cross into the bloodstream. Among this is calcium, which, because it is an element, cannot be broken down further. The elemental calcium in cheese, therefore, is the same as the calcium that forms your bones. Some other elements you might be familiar with are oxygen, sodium, and iron. The elements of the human body are, let's start with the most abundant one, which is oxygen. We also have carbon, hydrogen, and nitrogen. And each element's name can be replaced by a 1 or 2 letter symbol, and you will become familiar with some of this as we go on with the lecture of chemistry. And all the elements in your body are derived from the food that you eat and the air that you breathe. In nature, elements rarely occur alone. Instead, they combine to form compounds. So, what is a compound? Compound is a substance that is composed of 2 or more elements joined by chemical bonds. For example, the compound glucose is an important body fuel. It is always composed of the same 3 elements, which are carbon, hydrogen, and oxygen. Moreover, the elements that make up any compound always occur in the same relative amounts. In glucose, there are always 6 carbon and 6 oxygen units for every 12 hydrogen units. But what exactly are these units of elements? So let me discuss to you the atoms and the subatomic particles. So what is an atom? An atom is the smallest quantity of an element that retains the unique properties of that element. In other words, an atom of hydrogen is a unit of hydrogen. the smallest amount of hydrogen that can exist. As you might guess, atoms are almost unfathomably small. The period at the end of this sentence is millions of atoms wide. Atoms are made up of even smaller subatomic particles, and there are three types of which are very important. First is the proton, second is the neutron, and the third is electron. The number of positively charged protons and non-charged, or what we call as neutral neutrons, gives mass to the atom, and the number of each in the nucleus of the atom determine the element. The number of negatively charged electrons that spin around the nucleus at close to the speed of light equals the number of protons. An electron has about 1 to 2,000 of the mass of proton or neutron. This picture shows two models that can help you imagine the structure of an atom. In this case, helium. In the planetary model, helium's 2 electrons are shown circling the nucleus in a fixed orbit depicted as a ring. Although the model is helpful in visualizing atomic structure, in reality, electrons do not travel in the fixed orbits, but whiz around the nucleus, erratically in a so-called electron cloud. In the planetary model, the electrons of helium are shown in a fixed orbits depicted as rings, at a precise distance from the nucleus, somewhat like planets orbiting the sun. And in the electron cloud model, the electrons of carbon are shown in the variety of locations they would have at different distances from the nucleus over time. An atom's protons and electrons carry electrical charges. Protons with their positive charge are designated as P positive, and electrons which have a negative charge are designated as E negative. An atom's neutrons have no charge. They are electrically neutral, just as a magnet sticks to a steel refrigerator because their opposite charges attract. The positively charged protons attract the negatively charged electrons. This mutual attraction gives the atom some structural stability. The attraction by the positively charged nucleus helps keep electrons from staying far. The number of protons and electrons within a neutral atom are equal. Thus, the atom's overall charge is balanced. This time, I would like to discuss to you the atomic number and the mass number. An atom of a carbon is unique to carbon, but a proton of a carbon is not. One proton is the same as another whether it is found in an atom of carbon, sodium, which is Na, or iron, which is Fe. The same is true for neutrons and electrons. So, what gives an element its distinctive properties? What makes carbon so different from sodium or iron? The answer is the uniquely quantity of protons each contains. Carbon, by definition, is an element whose atoms contain 6 protons. No other element has exactly 6 protons in its atoms. Moreover, all atoms of carbon, whether found in your liver or in a lump of coal, contain 6 protons. Thus, the atomic number, which is the number of protons in the nucleus of the atom, identifies the element. Because an atom usually has the same number of electrons as protons, the atomic number identifies the usual number of electrons as well. In their most common form, many elements also contain the same number of neutrons as protons. The most common form of carbon, for example, has 6 neutrons as well as 6 protons for a total of 12 subatomic particles in its nucleus. An element's mass number is the sum of the number of protons and the neutrons in its nucleus. So, the most common form of carbon's mass number is 12. Electrons have so little mass that they do not appreciably contribute to the mass of an atom. So carbon is a relatively light element. Uranium, in contrast, has a mass number of 238 and is referred to as a heavy metal. Its atomic number is 92 and it has 92 protons, but it contains 146 neutrons. It has the most mass of all the naturally occurring elements. In this picture is a periodic table of elements. It is a chart that identifies the 92 elements found in nature as well as several larger unstable elements discovered experimentally. The elements are arranged in order of their atomic number with hydrogen and helium at the top of the table and more massive elements below. The periodic table is a useful device because for each element it identifies the chemical symbol, the atomic number, and the mass number, while organizing elements according to their propensity to react with other elements. The number of protons and electrons in an element are equal. The number of protons and neutrons may be equal for some elements but are not equal for all. Although each element has a unique number of protons, it can exist as different isotopes. So what is an isotope? An isotope is one of the different forms of an element distinguished from one another by different numbers of neutrons. The standard isotope of carbon is 12, commonly called as carbon 12. So carbon-12 has 6 protons and 6 neutrons for a mass number of 12. All of the isotopes of carbon have the same number of protons. Therefore, 13 carbon has 7 neutrons and 14 carbon has 8 neutrons. The different isotopes of an element can also be indicated with the mass number hyphenated, for example, C12 instead of 12C. And for hydrogen has 3 common isotopes. An isotope that contains more than the usual number of neutrons is referred to as a heavy isotope. An example is 14 carbon. Heavy isotopes tend to be unstable, and unstable isotopes are radioactive. So what is a radioactive or a radioactive isotope? It is an isotope whose nucleus readily decays, giving off subatomic particles and electromagnetic energy. Different radioactive isotopes is also called as radioisotopes, differ in their half-life, and at the same time, the time it takes for half of any size sample of an isotope to decay. For example, the half-life of tritium or tritium, which is a radioisotope of hydrogen, is about 12 years, indicating it's 12 years for half of the tritium or tritium nuclei in example or in a sample to decay. Excessive exposure to radioactive isotopes can damage human cells and even cause cancer and birth defect. But when exposed to controlled, some radioactive isotopes can be useful in medicine. In the human body, atoms do not exist as independent entities, but rather they are constantly reacting with other atoms to form and to break down more complex substances. To fully understand anatomy and physiology, you must grasp how atoms participate in such reactions, and the key is understanding the behavior of electrons. Although electrons do not follow rigid orbits a set distance away from the atom's nucleus, they do tend to stay within certain regions of space called electron shells. So what is an electron shells? It is a layer of electrons that encircle the nucleus at a distinct energy level. The atoms of the elements found in the human body have from 1 to 5 electron shells, and all electron shells hold 8 electrons except the first shell, which can only hold 2. This configuration of electron shells is the same for all atoms. The precise number of shells depends on the number of electrons in the atom. Hydrogen and helium have just 1 and 2 electrons respectively. If you take a look at the periodic table of elements, you will notice that the hydrogen and helium are placed alone on either sides of the top row. They are the only elements that have just 1 electron shell. A second shell is necessary to hold the electrons in all elements larger than hydrogen and helium. In this picture, electrons orbit the atomic nucleus at distinct levels of energy called electron shells. With 1 electron, hydrogen only half fills its electron shell. Helium also has a single shell, but its 2 electrons completely fill it. The electrons of carbon completely fills its first electron shell, but only half fills its second. Neon, an element that does not occur in the body, has 10 electrons, filling both of its electron shells. Another example is lithium, whose atomic number is 3, has 3 electrons. 2 of these fill the first electron shell, and the third spills over into a second shell. The second electron shell can accommodate as many as 8 electrons. Carbon, with its 6 electrons, entirely fills its first shell and half fills its second. With 10 electrons, neon entirely fills its 2 electron shells. Again, a look at the periodic table reveals that all of the elements in the second row, from lithium to neon, have just 2 electron shells. Atoms with more than 10 electrons require more than 2 shells. These elements occupy the third and subsequent rows of the periodic table. So the factor that most strongly governs the tendency of an atom to participate in the chemical reactions is the number of electrons in its valence shell. So what is a valence or a valence shell? It is an atom's outermost electron shell. If the valence shell is full, the atom is stable, meaning its electrons are unlikely to be pulled away from the nucleus by the electrical charge of the other atoms. And if the valence shell is not full, the atom is reactive, meaning it will tend to react with other atoms in ways that make the valence shell full. Consider the hydrogen. With its 1 electron only half filling its valence shell, this single electron is likely to be drawn into relationships with the atoms of other elements so that hydrogen's single valence shell can be stabilized. So all atoms except hydrogen and helium with their single electron shells are most stable when there are exactly 8 electrons in their valence shell. This principle is referred to as the Octet Rule, and it states that an atom will give up, gain, or share electrons with another atom so that it ends up with 8 electrons in its own valence shell. For example, oxygen with 6 electrons in its valence shell is likely to react with other atoms in a way that results in the addition of 2 electrons to oxygen's valence shell, bringing the number to 8. When 2 hydrogen atoms each share their single electron with oxygen, covalent bonds are formed, resulting in a molecule of water, or H2O. In nature, Atoms of one element tend to join with atoms of other elements in characteristic ways. For example, carbon commonly fills its valence shell by linking up with 4 atoms of hydrogen. In so doing, the two elements form the simplest of organic molecules, methane, which also is one of the most abundant and stable carbon-containing compounds on Earth. So, as stated above, another example is water. Oxygen needs 2 electrons to fill its valence shell. It commonly interacts with 2 atoms of hydrogen forming H2O. Incidentally, the name hydrogen reflects its contribution to water. So, hydro, water, gen is maker. I'll repeat, hydro means water and gen is the maker. Thus, hydrogen is the water maker. So this is it, our lesson for today about the elements and atoms, which are the building blocks of matter. And if you have any question, please write it down in the comment section down below. And thank you so much for watching this video and for listening to my discussion. Until my next lesson, bye everyone.